Welcome back to WABC. So we can move to another section of electrostatics. Okay, and the first question is a square loop of side 2 centimeter enters a magnetic field with a constant speed of 2 centimeter per second. That means the velocity, and the first one gives the idea about the area. Okay, the front edge enters at the field at t is equal to 0. Okay, that means when t is equal to 0, that means the time is 0. The front edge of the square loop is near to the magnetic field. Okay. So, which of the following graph correctly depicts the induced EMF in the loop? So, we want an equation to measure the induced EMF. That means the induced potential. Okay, so the loop is moving towards the magnetic field. So that magnetic field will link with the area of the loop and which produce a current. Okay, that means which produce a EMF, that means a potential. So which equation connect these quantities? EMF I will denote the EMF as E, that E is equal to minus BLV. Okay, so inside your textbook there is a problem which gives a area which is placed in a magnetic field, and this rod is easy to move, and while we are moving with a velocity v, we have a equation minus BLV. Okay, and v is the velocity, not potential. Okay, minus VLV. Okay, by using this formula, the velocity is constant throughout the motion and the velocity is 2 centimeter per second. We can change the unit of velocity into meter per second, that is 0.02 meter per second. That means 2 into 10 raised to minus 2 meter per second. And what is L in here? L is square loop of side length 2 centimeter, 2 into 10 raised to minus 2 meter. And what is B in here? B is magnetic field, and phi is 0.5 Tesla. Okay, so 2 into 4, 4 into 0.5 is 4 into 0.5 is 4 into 5 is nothing but 20, and decimal, by putting the decimal we get as the E as minus 2 into 10 raised to minus 2 multiplied by 2 into 10 raised to minus 2 multiplied by 0.5, which is equal to 4 into 0.5 is 4 into 0.5 is 2 minus 2 into 10 raised to minus 4. Okay, that means the negative quantity. When it will act, when the square loop is start to get 2 into the magnetic field after lifting, that means after moving out of that area, that that will be get discharged. That means the induced EMF get suddenly changed to 0. That means when it is entering, the value will be a constant throughout the area, and when the entire loop is inside the magnetic field, there is no change in flux, so then it will goes to 0. Okay, so after go to the 0, the loop is started to get out of the field, then a positive flux change will be there. So first of all it shows a negative EMF, and then it will show a positive EMF. So option B is the correct answer, and some people will like to put option A as the correct answer. That means when they will think that the loop is entering, when the loop is entering the magnetic field, the area is linearly increasing. Okay, but that is incorrect, because we have to calculate the rate of change of area. Okay, because of the constant velocity, the rate of change of area is a constant. Okay, if the square loop is moving with an acceleration, okay, that is correct. The rate of change of area is changing, that means increasing. So that will be a straight line. Okay, when if there is an acceleration, then this will be the correct. If there is a velocity, this will be the correct. Okay, so option B is the correct answer. So we can move to the second question. Okay, so in the situation shown in the diagram, so carefully observe the diagram. The magnitude of q, small q, is very less than the magnitude of the large q, and r, what is r? R is the distance between minus q and the center point of the dipole. Okay, r is very greater than, that means the minus q is placed very far away from the dipole, which is perpendicular in direction. Okay, the net force on the free charge minus q and the net torque on it about O at the instant shown are respective. So we need to calculate the net force and torque on the minus q. So what is force in here? What is force in electrostatics? We know that F is equal to, F has direction, so vector F is equal to K into Q1 Q2 by R square. See, all the terms as in R cube also. So in case of dipole, there is a chance to be in R cube, so don't worry about that. Okay, so first of all, we need to calculate the direction. See, options are with respect to the direction. In option A, the force is on the K direction. In option B is on the I direction. So option D is on the K direction. So I can define the direction as this is I, and this is J, and this is K. Okay, these are standard direction. Okay, so we can use this direction in here. So first of all, I am considering minus q, this one, and minus q, this one. Okay, so what's the force between these minus q and minus q? They are negative charges, so they will repel each other. So when I draw a straight line between them, it will repel. Okay, so because they are negative charge, so they will repel each other. And okay, so what is the force, direction of force between minus q and plus q? Minus q and plus q are same, opposite in direction, so they will attract. Okay, this minus q and this minus q are in same charge, that means the direction are changed same, that means both are negative, so both same type of charge will repel, that's why I pointed outward. And this minus q and this plus q, they are in opposite in direction, that means the charge are in opposite, so opposite charge get attract, so the force is towards this. And see, the magnitude F is equal to q1 q2, both are same, q1 q2 are same, and the r is same, because this is a and this is small r, so this distance is root of a square plus r square, both are same in here. So these two forces, if this is F1 and this is F2, the magnitude are same. Okay, and the magnitude are same, and what will be the resultant force? Resultant force is along this, because the magnitude are same, and the angle, this angle and this angle are also same. That's why, okay, that's why I am saying that this this direction will be the middle of this total angle, and that is along the I direction. So force is along I direction, positive I direction. So which option? Option A is negative K direction, and option D is positive K direction. So both are incorrect. Okay, and option B and C, the force is on the positive I direction. So there's a chance for the correctness in the B and C. Okay, then moving towards the torque. What is the equation for torque? Torque is R cross F. Okay, what is R? R is this length is R and it is directed towards J. So the direction of torque is the cross product of R and F. So the direction of torque will be J cross F is I, J cross I. J cross I is minus K, because in cross product I cross J is K and J cross K is I and K cross I is J. In the reverse, this is anti-clockwise, and in anti-clockwise direction that is positive. In clockwise direction, I cross K will be minus J and K cross J is minus I and J cross I is minus K. Okay, so by using this direction formula, we can say that the direction of torque is on the minus K. So which option? Option C is the correct. So option B is the wrong answer. So we don't want to calculate all the derivation. We don't want to do that actually. Actually we are please focus on the direction. Okay, so we can do this by normal calculation also. In calculation, by substituting these values, R is very greater than A, by assuming that R is very greater than A, by substituting this assumption in here, we get the magnitude of force as this. Okay, 1 by 4 pi epsilon 0 PQ by R cube. We easily get that value, but that is too lengthy. Okay, that is too lengthy. Please focus on the direction. Okay, to save our time. So we can move to the next question. The third question. A positively charged glass rod is brought near uncharged metal sphere which is mounted on an insulated stand. Okay, so this is uncharged. This is uncharged with a 0 coulomb of charge is placed in a insulated stand. Okay, if the glass rod is removed, okay, glass rod positively charged, positive is near to here. Okay, if the glass rod is removed, the net charge on the metal sphere. Actually, some correctness is to be needed in the question. Inside the question, some correction to be done. Actually, the glass metal sphere is earthed. Okay, initially it is earthed. Okay, and before removing this glass rod, we want to remove the earth. Okay, so by making, that means by putting the glass rod near to the sphere, this negative charge will come to near the positive charge. Okay, by attraction, opposite charge will get attracted. Okay, and after that we want to remove the earth. Okay, after that we want to remove the earth, and then we want to remove the glass rod. Then this negative charge will stays inside the sphere. Okay, in that case, in that question, the negative charge is the correct answer. But if the earth wire is not connected, initially earth wire is not connected, from where this negative charge can come? After removing the positive charge, after placing this positive charge, negative charge will come here and positive charge will here, and after removing the positive rod, they will get neutralized and there is no net charge will be 0. Okay, so if the sphere is connected by the earth initially, and before removing the rod, the earth should be cut off, and in that case the charge will be negative charge, or the answer will be 0. Okay, for this question the answer is 0, but the question is like this: when the sphere is connected by the earth, and then before removing the glass rod we want to remove the earth line, then the answer will be negative. Okay, so we can move to the fourth question. A parallel plate capacitor C1 with a dielectric slab in between its plates is connected to a battery. Okay, so this is a capacitor and a dielectric constant. A slab of dielectric constant is placed inside it. It has a potential, and at this time it is C1, and this is connected to a battery of potential V1. It has a potential difference V1 across its plates. When the dielectric slab is removed, keeping the capacitor connected to the battery, the battery is still working in here, and we have to remove this dielectric slab. The new capacitance and the potential difference are C2 and V2 respectively. Then, okay, the new capacitance is C2 and the new potential is V2. See, what is the equation for the capacitance? Capacitance is equal to epsilon 0 A by D. Okay, if there is no dielectric constant. If there is a dielectric constant, capacitance is equal to K epsilon 0 A by D. So, capacitance will get decreased. So, C2 is lesser than C1. C2 is lesser than C1. So, which options are correct? Option A and option B are seems to be correct. Okay, and what happens to the voltage? Since before and after the capacitor is connected to the same voltage source, so V1 equal to V2. So, option B is the correct, option A is wrong, because see, the capacitor is not changing from the source. Okay, the batteries, the same battery is used to charge the capacitor. So, V1 is equal to V2. So, we can move to the fifth question. A cubical Gaussian surface has of length A is equal to 10 centimeter. Okay, you can see the figure cube. Length A is equal to 10 centimeter and electric field lines are parallel to x axis. Okay, yes, correct. The magnitude of electric field through the surface ABCD. Okay, I will draw the ABCD. This is ABCD and these are the lines which entering. So these are the lines which entering ABCD, and EFGH are 6K Newton per coulomb and 9K Newton per coulomb. So through this side it is 6K Newton per coulomb and through this side it is 9K Newton per coulomb respectively. Then the total charge enclosed, so we have to calculate the total charge enclosed by this cube. Okay, so there is a change in field lines which is going out and coming in. Okay, so what's the change in field lines? What's the change in flux? The change in flux is 3K Newton per coulomb. Okay, so change in field lines, that means the change in electric field, that is the change in field lines, that means the change in electric field, that means the electric field inside the electric field contributed by the charge which is inside the cube is E is equal to 9K minus 6K is 3K Newton per coulomb. That means 3 into 10 raised to 3. 3 into 10 raised to 3 Newton per coulomb is the electric field given by the charge inside. Okay, so we have electric field and we have to calculate the charge. So how we can connect the electric field with the charge? Yes, we know that flux is what? What's the equation for flux? Q by epsilon 0. So what is Q? Flux into epsilon 0. Before going to that, we have to calculate the flux. We have the electric field. So what is flux? Electric field dot product with the area. And what is area? 10 centimeter, cube of 10 centimeter, side 10 centimeter. So what is area? 10 centimeter into 10 centimeter. That means 0.1 meter into 0.1 meter. That is 0.01 meter square. So the area is 0.1 meter into 0.1 meter, which is equal to 0.01 meter square. The area is 0.01 meter square. So the flux is 3 into 10 raised to 3 multiplied by 0.01, that is 30. The flux is 30. Okay. Area is meter square and electric field is Newton per coulomb. Newton meter square per coulomb is the unit of flux, and then flux is multiplied by epsilon 0. So Q is equal to, total charge Q is equal to 30 is multiplied by, what is the value of epsilon 0? Approximately is 8.8 into 10 raised to minus 12. Okay. So 3 into 8 is 24, and 0.8 we can say that approximately we can add 3. So 3 into 8.8 is approximately 27. Okay. And multiplied by a 0 into 10 raised to minus 12. Okay. So what are the options in here? Okay, options are in a nano coulomb. Okay, nano coulomb, that means 10 raised to minus 9. So we need to change, which is equal to 0.27 into 10 raised to minus 9 coulomb. That is equal to 0.27 nano coulomb. Okay. So which option is the correct? 0.27 nano coulomb. Option B is the correct, and option C is minus. Why the answer is not in negative side? Okay, because the change in electric field is a positive. The leaving electric field is 9K. Okay, and the incoming electric field is 6K. So that the difference is 3K. Okay. So if the incoming is 9K and the outgoing is 6K, then the change in electric field will be minus 3K. Okay, that's why the option B is the correct answer. Otherwise, option C get the correct answer. Okay, so now the option B is the correct answer. So we can move to the sixth question. Okay, sixth question is a very good question. So read the question. Electric field at a distance r from an infinitely long uniform charged straight conductor. So first of all, we want to consider an infinitely long charged straight conductor. Okay, electric field at a distance r. This is at a distance r. Electric field E is equal to having a linear charge density lambda, that is E1. E1, that they have named that as E1. So what's the value of E1? E1 for a, that means the electric field at a distance r from a infinitely long straight conductor, E1 is given as lambda by 2 pi epsilon 0 r. Okay, that means E1 is equal to 1 by 2 pi epsilon 0 into lambda by r. This is a standard derived formula which is given inside the textbook. You can refer it. Okay, and what's the second case? Another uniformly charged conductor having same linear charge density lambda is bent into a semicircle of radius r. Okay, this is the having same linear charge density lambda is bent into a semicircle of radius r. This is circle, so semicircle will look like this. Okay, and radius r, this is radius r. Okay, the electric field at its center is minus E2. The electric field is minus E2. Okay, so what is E2? E2 is minus of E, electric field at the center. Okay, what is the electric field? What is the equation for electric field at the center? E is equal to minus 1 by 4 pi epsilon 0 to lambda by r. Okay, this is the equation for the electric field inside at the center of a semicircle of line which have a uniform charge density as lambda, that is lambda, the electric field is minus 1 by 4 pi epsilon 0 into 2 lambda by r. Okay. So how we can connect? So what's the value of E2? E2 is minus of this E, minus 1 by 4 pi epsilon 0 2 lambda by r. Okay. So E2 is equal to 2, we can cut a 2 from both. So 1 by 2 pi epsilon 0 and minus will be cancelled each other. So 1 by 2 pi epsilon 0 into lambda by r. Okay. So what is E1? E1 is lambda by 2 pi epsilon 0 r, and what is E2? 1 by 2 pi epsilon 0 lambda by r. So E1 is equal to E2. Which option is the correct one? Option A, E1 equal to E2 is the correct option. Okay. So can we move to the next question? Yes. So the 7th question is, okay, a uniform electric field vector E exists along a horizontal direction. So the electric field is given as E, this one. The electric potential at A is VA, so this is VA, and at B is VB. Okay. A small point charge Q is slowly taken from A to B along the curved path as shown. Okay. So see, we can say that the potential at here, this in this line is same, and the potential at this is same. Okay. So but in this A and B, the potential at A and B are different. So a work is to be done to change the potential field. Okay. What is equipotential surface? The surface which have equal potential, and in here the A and B have different potential. So a work is necessary to do the to move a charge from one potential to other potential. It is irrespective of the direction. It is irrespective with the value of the potential. Okay. So we can move through the straight line. Actually we can move through a different path. Both are same. Both have to do the same work. Both have to spend the same energy to move the charge from this position to this position. Okay. So I am saying that V is the final potential minus VA is the initial potential. Okay. Change in potential, that is equal to Q into, that means the magnitude, minus Q is actually a small point charge Q is slowly, so not minus Q, so plus Q into electric field. Okay. Into electric field. So Q is changed through this direction. So that change in potential is equal to E into minus E into X. X is the distance moved, and E is the electric field. Okay. Equation for the electric field is 1 by 4 pi epsilon 0 Q by R square. Okay. In order to get the potential, we want to multiply with the charge and divide by multiply with the distance. Then it will gives what? Q1 Q2 by Q by R. Okay. In order to get the potential from the electric field, actually it is by electric field is proportional to Q by R square, and it is multiplied by a distance. Okay. Then the distance and the power factor will get cancelled. That means if we multiply by a R, so so the potential is proportional to Q by R. So okay, so we need to calculate the energy, potential energy. Then to calculate the potential energy, we need to multiply this by a Q. Okay. Then only we get a potential energy. So the potential in here VB minus VA is related to the electric field E, because the negative sign is actually it is in the direction of electric field. The charge is moving in the direction of electric field. That means the final potential minus initial potential is negative Ex. So what is VB in here. The final potential is VA minus EX. Okay, then it is multiplied by AQ. Potential energy E is equal to, potential energy U. Potential energy U is equal to QB. That means the final potential energy Q into VB, that is VA minus EX. Why does I give the negative sign for E is we have to calculate the potential energy at the final. Okay, the potential energy of the charge when it is at the point B, that's why it is minus. Okay, so option C is the correct answer. Okay, so we can move to, okay, this is our last question in this section. Bye.